Okay, dynamic equilibrium. Dynamic equilibrium. Dynamic equilibrium. Right, so when you have a reaction, for example, if you take this reaction here. Now, do you know the name of this reaction? The famous, very well-known reaction. Everything is in the gaseous state. This is called the Haber process. Some people pronounce it Haber process. And it's used to make ammonia, and ammonia is used to make fertilizers. Industrially, a very important reaction. Now, when you see an arrow like this, what does that actually mean? It does not mean that the reaction is in equilibrium. That arrow just means that the reaction is reversible. That's all that it means, that the reaction is reversible. So it can go in the forward direction, we call that the forward direction, and the reverse direction. Okay, so what does dynamic equilibrium actually mean? When you see this sign, it doesn't mean that it's automatically in dynamic equilibrium. So what does it actually mean? So dynamic equilibrium means, the word dynamic means constantly changing, constantly moving. I mean, the opposite would be static, where it's not changing at all. And dynamic equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction. The rate of the reverse reaction. Okay, and that's what dynamic equilibrium means. The rate of the forward reaction equals the rate of the reverse reaction. Okay, so if you've got reactants going to products, then that actually means that at exactly the same time, reactants are forming products and products are forming reactants. So it's going like this at exactly the same rate. Exactly the same rate. So if you imagine reactants here, products here, at exactly the same rate, it's moving like this. Okay, so it appears that nothing is changing, because if you had, say if you had 3 things here and you had 2 things here, okay, and then it's going at exactly the same rate, you will always have 3 things here and 2 things there. The rate is the same, it's equal. Okay, so it appears that nothing is changing. So how do we know when a reaction is in dynamic equilibrium? How do we know that a reaction has reached dynamic equilibrium? Now, quite often we just drop the word dynamic. Okay, we just tend to drop that word and we just call it equilibrium. Okay, so if we take a container, okay, now, and we put in some reactants into the container, okay, and dynamic equilibrium can only be reached, a state of dynamic equilibrium can only be reached in a closed system, or we sometimes call it an isolated system. They mean the same thing. Sometimes we call it different things, but it means the same thing. A closed system or an isolated system. That means that no material can enter or leave. When we say material, we mean chemicals. So no material can enter or leave. And it's called a closed system. Okay, so we've got some reactants in a container, and we're going to close a system, an isolated system. Okay, so container, put some reactants in, close it up, and then we leave it for whatever time is necessary, and we come back to it, and it has now reached equilibrium. What is going to be inside the container? So this is that's initial. What's going to be inside at equilibrium? what's going to be inside the container. Because we've left it for a week, whatever time, what's going to be inside. There's going to be products as well as reactants. There's going to be products in the container too. Okay? How can we tell, how do we know that a reaction has reached dynamic equilibrium? Well, because the rate of the forward equals the rate of the reverse, and it's going at exactly the same rate, the concentration of the reactants and the products are constant. Don't say they are the same, because they are not the same as each other. Use the word constant. It looks like nothing is happening because the concentration of the reactants and the products are the same, are constant, but it is continually moving. Okay, so how do we know that a reaction has reached dynamic equilibrium? We measure the concentration of the reactants and the products, and if they are constant, if they are not changing, then it has reached equilibrium. Okay, so that is what equilibrium is. Now there's something else called the position of equilibrium. Okay, just get another piece of paper. The position of equilibrium. So if we go back to the same reaction again. So if we have a container, okay, and we put some reactants in the container, some reactants, whatever the reactants are, we close the container, so it's an isolated closed system. We leave it, so that's initial, at the start. We leave it for a set time, maybe a week, come back to it. There are also now products in the container. There's products in the container. And we know it has reached equilibrium because the concentration of the reactants and products is not changing. It's constant, it's not changing. Okay, it's constant. And we know it's reached equilibrium. Okay, now there's something called the position of equilibrium. Position of equilibrium. Position of equilibrium. Okay, and we sometimes abbreviate that as POE. But in an exam paper, I wouldn't write POE in an exam paper. Just in my notes, I would write POE. The position of equilibrium. Now, the position of equilibrium tells us about the extent, equals the extent of the reaction. It tells us how far, which means it tells us how far the reaction has progressed. Okay, so if you have reactants forming products, we need to know how far the reaction has progressed, the extent of the reaction. Okay, so if the position of equilibrium, POE, position of equilibrium lies on the left, that's not good. That means that there are more reactants. It means that the reaction has not progressed very far, has not moved very far. The extent of reaction is not very great. So if the position of equilibrium lies on the left, so this is the left and that's the right, so that means that there are a lot of reactants in the container, and that it hasn't progressed very far. Okay, if the position of equilibrium lies on the right, then that means that if the position of equilibrium lies on the right, that means that there's more products in the container, and that's a better reaction because you want products. That's the whole point of doing a chemical reaction, is that you want products. So you want the position of equilibrium to be on the right. Okay, so in this example I've given here, at equilibrium, this is at equilibrium, there are 5 products and only 3 reactants. There are more products, so I would say the higher concentration of products, so I'd say the position of equilibrium lies on the right. Okay, now, so when you're doing a chemical reaction, when you're planning a chemical reaction, You want as much product as possible, because that's the whole point of doing the chemical reaction. You want product. So you need to change the conditions. You need to change the conditions. And when we say conditions, we mean temperature, concentration, pressure. If it's a gas, that's only for gases. Change the conditions in order to move the position of equilibrium, to the right, and therefore get more products, Okay, so what we need to do is we need to change the conditions. We need to change the temperature, the concentration, the pressure in order to move the position of equilibrium to the right so that we get more products. Now there's something that you need to know called Le Chatelier's principle. Okay, so the definition, you need to know this. It's after the guy who came up with it. Le Chatelier's principle. So just be careful with your spelling. Le Chatelier's principle, and you need to learn this word for word, okay? And the principle is, it's in your textbook as well, when a system in dynamic equilibrium, is subjected to a change, and we mean change, we mean concentration, pressure, temperature, subjected to a change, the position of equilibrium will move, to minimize the change. Okay, so that's Le Chatelier's principle. So it's basically saying that if you change something, the equilibrium will oppose this. It'll move in it'll do something opposite to minimize the change. So for example, if you increase the pressure, it will move in the direction, the equilibrium will move in the direction that will decrease the pressure. If you increase the temperature, the position of equilibrium will move in the direction that will decrease the temperature. We'll do the opposite of what you've done. Okay, so we need to see this as in an actual example. So let me give you an example to see this in practice. Okay, so let's do a couple of examples now. Right, so let's take this example first. Okay, so we're going to look at increasing the concentration first. If we increase the concentration, what happens? Okay, so we're going to take this reaction here, and you tell me if you recognize what this reaction is. So it's ethanol and ethanoic acid, and that is going to make ethyl ethanoate plus water, an ester plus water. So it's called esterification, is this reaction. Esterification. Okay, making an ester. All right. So say if we increase the concentration, so I'm going to go like that, increase the concentration of the ethanol. Okay. What is going to happen to the position of equilibrium? What is going to happen to the position of equilibrium? Right. So we've got a container, and all these chemicals are in the container. They're all in the container, reactants, products, all in the container. We're going to take the lid off the container, take the lid off, and we're going to put more reactant in. We're going to put more reactant in. It is not in equilibrium anymore, okay? The rate of the forward does not equal the rate of the reverse, because we've messed about with it. We've taken the lid off, we've put more reactants in. So now the forward, because we put more reactants in, the forward reaction is now going to be faster than the reverse reaction. But at some point, the equilibrium will restore and will come back to what it should be. Okay. Anyway, we've put more reactants in. We need to minimize the change. Le Chatelier's principle that the position of equilibrium will move to minimize the change. The position of equilibrium will move to the right to remove, to use up the chemicals that we've added. So the position of equilibrium will move to the right. Okay? Let's try something else. What if we decrease the concentration of ethanol? Okay, what if we took some ethanol out of the container and we decreased the concentration of ethanol? If we decrease the concentration of ethanol, the position of equilibrium will move to the left to put the ethanol back in again, to restore the ethanol, to minimize the change. Okay, what if we increase the concentration of the product, the ester? Okay, what if we increase the concentration of the ester? Which way will the position of equilibrium move? We put more ester into the container. This is the ester here, this one here. Put more ester into the container. The position of equilibrium will move to the left to minimize the change, to get rid of what we have done by putting more ester in. Okay. Here's another question. Here's another one. So, pressure. That's concentration. The effect of concentration on equilibrium. What about the effect of pressure? Okay. So, what about the effect of pressure? And pressure is only for gases. So, we're going to take this reaction here. All gases. Ammonia, 5 oxygens, plus 6 waters, all gases. Okay, right. So this is all in a container. It's all inside one container. We've left it to reach equilibrium. There are reactants, there are products, all inside one container. And what we're going to do is going to increase the pressure. Increase the pressure. Okay. What do we practically have to do to increase the pressure? So it's in a container and we want to increase the pressure on this reaction. We just put it into a smaller container. We just put it into a smaller container and that is increasing the pressure. Okay? So if you put it into a smaller container, you are pushing all the molecules closer together. They've got less room to move around. You're pushing them closer together. So to imagine it's like in your room and the walls, and you've got lots of people in your room. So therefore, imagine a classroom. You're in your classroom. There's lots of people in the classroom, and then the walls of the classroom start to come in, and the ceiling comes down, and the floor starts coming up, and you're all getting squashed closer together. In order to minimize, in order to reduce that, you need less molecules in there. Less molecules will minimize, will overcome what the increased pressure. Okay, so increased pressure goes to the side, favors the side with fewer molecules. It'll move to the side where there are less molecules. Okay, with fewer molecules. So in this reaction we've got here, we've got 4. Doesn't matter what the gas molecules are. Look at the numbers at the front. We've got 4, we've got 5, we've got 9. We've got 9 molecules on this side, gas molecules, and we've got 10 gas molecules on that side. So if we increase pressure, the equilibrium will move to the side with fewer molecules. So the position of equilibrium will move to the left, which is not a good situation because you want it. That's not really very good. You want it to move to the right. Really, will move to the left. Okay, yeah, and then decreased pressure, which is just the opposite. Decreased pressure is when you put it in a really big container. You just change the container and put it in a big container. So again, think about your classroom. If your classroom, all the people in your class, what if your classroom was a big, enormous hall? And there's just 15, 20 of you, and it's a big, enormous hall with lots and lots of space. To overcome that, you need more molecules in there. You need more molecules to minimize the change. So decreased pressure will move to the side with more molecules. All right. Okay. Last condition. We've done concentration. We've done pressure. Let's just quickly do temperature. All right. So let's go. let's do a temperature one. So I need an example. All right. So let's take the Haber process. Okay, here's a good example. All gases. Okay, all gases. Gas. Sorry, two ammonia gas. Delta H equals minus 92 kilojoules per mole. Okay, sorry. Okay, there. Right, that's a Haber process. Right. Okay, so we're going to increase the temperature on this reaction. We're going to put a Bunsen burner underneath it and increase the temperature. Okay, so you will want the reaction, the equilibrium will move in the direction that reduces the temperature, that does the opposite. If you increase the temperature, the equilibrium will move in the direction that reduces the temperature, okay, which is the endothermic, the reaction that absorbs the energy, okay. Increased temperature favors the endothermic direction, the one that absorbs the energy enters. If you've got a minus here on the enthalpy change, that means that the forward direction is exo. Therefore, the reverse direction must be endo. So increased temperature favors the endothermic. That's the reverse is the endothermic. So if you increase the temperature, the position of equilibrium, this is the left, this is the right, as you're looking at it, the position of equilibrium will move to the left. Okay, position equilibrium will move to the left. Right, so finally, we mentioned concentration, we mentioned pressure, we mentioned temperature. Catalyst. What happens to the position of equilibrium when we add a catalyst to a reaction? Okay, catalyst has no effect on the position, of equilibrium. You just you reach equilibrium quicker. You just get there quicker. It has no effect on the actual position. You reach equilibrium quicker because it speeds up both the forward and reverse reactions equally. Right. So, final question for you. Right. This is final question. So let's say we've got this reaction, which is part of the contact process. Just need to balance it. One of the steps in the contact process. Put 2 there, put 2 there. Okay, it's called the contact process. It's industrially a very important process. It's used to make sulfuric acid. Okay, now I can't quite remember what the enthalpy change is, but it's negative. So I'm going to put X because I can't quite remember exactly what the value is, but it is negative. All right. So the question is, theoretically, I want to get the highest yield possible of sulfur trioxide. I want the highest yield possible of sulfur trioxide. Highest yield possible of sulfur trioxide. Which conditions should I use? What are the conditions I should use to get, theoretically, to get the highest yield? So the conditions that I need. So first, they're all gases. These are all gases. Okay, so what kind of pressure? There are three molecules of gas on this side and 2. Okay, so if I use a high pressure that favors a side with fewer molecules, fewer molecules, therefore the position of equilibrium, there's only 2 here, will move to the right. That's good, that's what I want. I want a high yield. I want the position of equilibrium to move to the right. The forward reaction is exothermic, so therefore that's exothermic, so therefore I need a low temperature. A low temperature favors the exothermic side. Okay, low temperature favors the exothermic side, and a low temperature, therefore the position of equilibrium will move to the right. Okay, when you're thinking about temperature, right, say if we said that this line here, that's equilibrium, right, and the thermometer temperature increase up in here, okay, right, and then we put a Bunsen burner and we put some heat underneath it, yeah, and we increase the temperature of the reaction, of the whole reaction, we increase the temperature. Then we need, if we increase the temperature, then we need the reaction that absorbs the energy, that will bring the temperature back down. So the endothermic, yeah. So similarly, if we lower the temperature, if we put it in the freezer, and we lower the temperature, we want the reaction that is going to increase the temperature. We want the exothermic one.